In the last video, we had been about to calculate the tan of negative 480 degrees. In order to do that, we said one of the easier ways would be to add multiples of 360 to negative 480 until we could use our reference rules. So a negative 480 plus 360 is still negative 120. I can't have a negative angle to use my reference rules, so I'll add 360 again. When I add 360 a second time, I get 240 degrees. Now I can use my reference rules for an angle in the third quadrant, and that angle of 240 degrees would have a reference of 60. So I'm calculating the positive tan of 60 because tangent in the third quadrant is positive. Once again, the tangent of 60 is a rad 3. And now I can calculate the algebra involved. I have a fraction and a whole number, and I'd like to combine them with subtraction. In order to do that, I'll need a common denominator. I'll choose the common denominator 2. Multiplying this entire second term by 2 over 2 gives me 1 over 2 minus 2 rad 3, also over 2. And this would be my combined, simplified, single fractional term. Finally, on our agenda, we need to take the anti-trig function, or the inverse trig function, and find the angle to which it belongs. This is probably the hardest of our 4 jobs, and so I'll do these questions each with you one at a time. The first thing that I need to do is to rewrite example J as an inverse function. I say inverse, you say switch, and so when I apply the inverse trig function, that means that the point 2756 and the angle theta have switched positions. This now tells me exactly what I need to type into my calculator, and I will type the inverse sine of 0.2756. As long as I'm in degree mode, the angle that I will get is 15.99777,343. Now, that angle, rounded to the nearest degree, is roughly 16. But 16 is not an angle in quadrant 2. This is where life gets tricky. I now need to take that 16-degree angle and draw it in as a reference angle that happens to lie in a bow tie triangle in the second quadrant, meaning this angle right here will be 16. That is the angle in the bow tie whose sine is 0.2756, but it's not the angle I'm looking for. Now I'm going backwards with my reference rules and saying this is actually the angle that I'm looking for. Once again, it would be the supplement of that 16-degree angle, and that angle is 164 degrees. That means that if I were to take the sine of 164 degrees, which is a second quadrant angle, I would get 0.2756. Let's try another. The first thing that I want to do is write this as an inverse function. I'll put in the inverse notation and switch the answer value with the angle name. I'll now take that inverse cos value that I've written and type it into my calculator to get that theta is roughly equal to 11 degrees. Once again, 11 degrees would have a cosine of 0.9816, but it's not an angle that happens to lie in quadrant 4. So I draw the fourth quadrant bow tie angle, and I make the reference 11 degrees. Once again, this is a triangle that would have a cosine of 0.9816, but it's not the angle that I'm looking for. The angle that I'm looking for is the one that is just 11 degrees shy of being a full circle. Using my reference rules backwards, what I'm doing is saying that 360 minus the angle I'm looking for would give me 11. To solve for that algebraically, I'm going to add theta to both sides and subtract 11 from both sides, and I'll discover that theta is actually 349 degrees. That means that if I were to take the cosine of 349 degrees, I would indeed get 0.9816. In the next example, the first thing I want to do is rewrite this tangent function as an inverse whose answer is -7, I'll put that in parentheses, and whose angle value would be named theta. Typing in the inverse tan of -7 gives me an angle of -82. Now I have several problems. Theta, and this, by the way, is an adjusted or rounded angle, is a negative angle, and it's not in quadrant 2. If I were to draw a -82 degree angle, I would get an angle that lands down here. What I'd like is an angle that's over here somewhere. In order to fix this, I'm going to use 82 just as a reference angle. The negative in this case just told me that the answer belonged in quadrant 4. The reason that the answer belonged in quadrant 4 is because tangent in quadrant 4 will always be negative. Your calculator has to choose a quadrant when it's determining inverse functions, and typically it will always choose quadrants 1, 2, or 4. The reason it does this is because if it's in quadrant 1, it's an acute angle. If it's in quadrant 4, it can be an acute angle, it'll just be negative. And quadrant 2 is used when cosine is negative, because if you'll recall, cosine is always positive here, and cosine is positive here. So the two quadrants that would give me acute angles are not options for a negative cosine. In any event, I'll use this 82 degrees as my reference angle, just dropping the negative because I know it's just a direction. And I'll draw a bow tie angle of 82 into the second quadrant. Now I'll be looking to find the angle that starts in standard position and goes around to that 82 degree angle. My rule for references in the second quadrant is to take 180 minus the given angle to get my reference. Algebraically solving for the given angle means to add theta to both sides and subtract 82 from both sides. And that tells me that my reference is actually, my given angle was actually a 98. Let's do one last problem together. In this last example, step 1 will be write it as an inverse function. Notice I'm putting parentheses in so that I don't lose that negative. And now I'm going to go to my calculator and type what I see. I get an angle of -4, and again I have rounded, and I'm going to use a picture to visualize this. This -4 means go south 4 degrees, but the reference is really just a 4. If I wanted to put that angle into quadrant 3, it would still be a 4-degree angle, it would just land over here. And the given angle, that would be 4 degrees beyond the x-axis in quadrant 3, is an angle of 184 degrees. That means if I were to type the sine of 184 degrees, keeping in mind that I rounded this value, I would get a number very close to -0.0698. all for now. We'll be doing a lot more with this last section in class very soon.